right, good morning, everyone. Let's get going. I'm sure some people will also join in a bit. Welcome back to another installment of the BEG seminar series. Today we have one of our own, Carlos Uroza from the Venezuelan branch of the BEG. Carlos is a senior geologist with more than 20 years of industry experience in oil and gas. He worked with Halliburton Consulting in the Middle East, Equinor Statoil offshore project in offshore Mexico and Gulf of Mexico, ConocoPhillips in Nigeria and Gulf of Mexico, and PDVSA in eastern Venezuela. He has an MSc Geology from Queensland University of Technology in Australia and a PhD from here at UT Austin. He's a sedimentologist and stratigrapher by background, and from February of 22, he has been working with the GCCC here at the Bureau, focusing on the evaluation of geological sites for CO2 sequestration along the Gulf Coast area, USA. And with a related topic here, assessing the CO2 sequestration potential of the Paleogene Wilcox Group onshore Texas, USA. Carlos, take it away.
Okay, thank you. Thank you everybody for coming and those ones that are online. Well, I'm going to be presenting on behalf of wait. Want to go back? Okay. So I'm going to be presenting also on behalf of my colleague. This is and actually it's still work in progress because we have been doing a lot of work in the Wilcox, but the Wilcox is a huge depositional system, and the transect that we are investigating is more than 500, it's like a 590 kilometer. So it goes all the way from southwest Texas all the way to the boundary with Louisiana. So, and I would like to thank my co-authors that have been working with me through the evolution of this project, and the contribution that, for instance, Bill Ambrose, we have been using his code description in some of the course that he got, and some of my former students that have been coming also in going through the project. Basically, the funding for this project mostly came from the CCAR USA initiative. That is the DOE funding, but we are still doing some work on behalf of using some different funding from somewhere else. So what we are going to be basically covering here, I'm going to be describing the area of interest, talking about the stratigraphy and structure framework of the Wilcox Group, sand mapping and depositional environment, the reservoir quality and implication for CO2 storage injectivity, some of the constraints on the CO2 storage, that is the USDW, that is basically the underground sources of drinking water, the overpressure, the legacy well, and one example of the capacity estimation, and then some conclusion. Why this is relevant? I'm going to move here, it's easier. Why this is relevant is because basically, you know, the Wilcox is a coarse-grained clastic system. There is thick sandstone units and high injectivity. I mean, you will see when we talk about the porosity and permeability. It is valuable because it has proximity to CO2 sources, and actually it's an opportunity to evaluate how a deep recharge of fresh water can create uncertainty in defining a storage target. That is actually one of the problems that we have in the Wilcox, and that's one of the problems that companies, they want to go, I mean, at the moment, companies, they are kind of away from the prospectivity of the Wilcox for CO2 sequestration because we have a very deep aquifer. I mean, we have a recharge. Keyboard, yeah. Yeah, click the wrong ones. Yeah, okay. So, I mean, it is a huge area. Basically, you know, there is good opportunity for CO2 sequestration here. And The Wilcox has been studied in the past. Many people has done a lot of work for oil and gas, for geothermal, but in this case, this is the first time we are doing an investigation of the potential for CO2 sequestration. And we see, emissions, CO2 emissions, what you see here, or these are the CO2 emissions, like for instance, Travis and Besar County. So there is a good amount, even this area, the hosting area. So we can, potentially, we can find injectivity also in some of the areas that are close but the stratigraphy that is, like for instance, below us here, there is a lot of carbonate that are tight really for CO2 sequestration. So basically, when we move south, the first wedge of sand that we see is the Wilcox. So that's the idea also that we have been looking for this work. Okay, this is the transect. It's like a more 500 and something kilometers. So what you see also, I'm highlighting here some of the cores that we have been investigating. These are here. Deception, this is the approximated area, that is this area here. There are two main problems here. One is that to the north of the transect, we have the USDW. So basically we need to map the USDW. When we go south of the transect, we have the overpressure. So basically it is like a corridor. But the Wilcox continue depositing to the south, but as the Wilcox goes deep, one thing, there is the deterioration of reservoir quality, and also there is overpressure. So basically those are two things that we cannot take into account for CO2 sequestration. The stratigraphy of interest, so here, this is from this publication. So, and this is mostly from this area, from the western area. So basically we had the lower Wilcox, middle Wilcox is the seal for the lower Wilcox, and we had the upper Wilcox, and we had the wreck low shell as the seal for the upper Wilcox. So those are the two main wedges that we are investigating, lower Wilcox and upper Wilcox. There is not much prospectivity in the middle Wilcox because it's kind of shaly. And one thing to make it easier, the analysis along this long transect, we subdivide the area into, we subdivide the transect into three areas. What we call the western area are all these counties south of Lavaca County. And there is, good knowledge actually, because Julia, she's one of my colleagues, my co-author, she has been investigating the Guadalupe Delta, for instance, for many years. So there is a good knowledge, good literature about how is the Wilcox in this area. In the central area, there is not much investigation, so there is a good core here, 2,400 feet of core that Bill Ambrose described, and we have been incorporating that to the analysis. And there is a lot of area here for CO2 sequestration, and basically it's coming from the Colorado and Paleo Brazos Delta. As we move to the northeast, there is also room, there is a lot of room for sequestration, but there are some constraints also in the overpressure. So basically that's what we call the eastern area. There is still a lot of work to do in the eastern. They have not done, we didn't find, very little work actually was done in the past in all this area regarding the Wilcox knowledge. So this is an stride-oriented correlation across the, this is basically from the western and central areas, and all these counties from McMullen and Leaf Oak all the way to Waller County. So here are the wells that we use. In this case, we had 11 wells here. Important things in this figure is that we had the mid-weight shell here. That is the major transgression before Wilcox time, and then we had all these wedges, sand wedges. That this is this is all the lower Wilcox, for instance, and this is the middle Wilcox, and this is the upper Wilcox. We are using here the nomenclature that we have already in the literature. And Julia and some colleagues in the past, they subdivide the lower Wilcox, for instance, into three major delta systems, what we call delta A, B, and C. Okay, so basically we had that subdivision, and we are using that subdivision along the transit. Doesn't mean that those deltas are, continuous, because if you see here, and this is a cartoon that Fisher and McGowan they did in the 60s. I think we had tried to redraw these things, but actually this is essentially what they did. So if we see here those deltas, the Guadalupe, Colorado, Brazos, Trinity, Angelina, Natchez, and Sabine deltas. And those are the entry points. I mean, those are the wedges, those are the sand wedges, and those are the things that we are investigating actually. Because things that you need for sequestration, for CO2 sequestration, we need thick sands, we need thick packages of sand because we need to have, volume. We also need good injectivity, we need good permeability, because if we don't have good permeability, there is no way we can go and inject CO2. And also we need some kind of seal. In this case, for instance, the lower Wilcox, we had this big shell here, no? And this is a continuous layer, marine shells. So there is some kind of continuity here. So this could be like the confinement unit for CO2 sequestration here. However, we don't need to have a real seal. Like in the oil industry, we need to have a seal. But in this case, we have a lot of layering within the lower Wilcox and within the upper Wilcox. And that's basically, all this layering also help to distribute the CO2 plume when you are injected laterally. And these things, that's what Alex Baum has published in the past about the confined system that he has done publication on that. This is another cross-section now going from the central area into the eastern area. So again, you see here in the Paleo-Brazos Delta, you see a lot of thickness. I think let's go back very quick to this one. One thing that I forgot to tell here. So you see here in this Guadalupe Delta, for instance, the lower Wilcox is not very sandy as we see here in this Colorado Brazos Delta, where we see those thick packages. Thick packages here, sand, these are more opportunity for CO2 sequestration. Okay, now it is saying in the central area, again here, we see a lot of thickness packages, both in the lower Wilcox and the upper Wilcox. As we move to the northeast, we still see a lot of sand, but there is kind of more layering. You can see here, there is more intervening shells within the stratigraphy. We did some, seismic, we are very constrained for seismic data because there is no much onshore seismic data. So basically we are using some of the transect from the ion 2D seismic, and this is one part of the seismic. So basically what you see here, this is the top Wilcox, the lower Wilcox, these two horizons. So you see all this down to the basin fault. These are all this extensional regime. That is basically what we see here. We don't have much complication for salt tectonic here, for instance. So basically the complication is just this groove faulting that many of you that are familiar with the Wilcox know about this. So one thing, there is groove, yeah. For instance, in this compartment, this upper compartment, as we go down, you can see the arrow, and as you go continue down, this, of course, this fault, they are laterally extensive, but they are, kind of arc weight actually. And then they have this down to the basin component, and then there is a groove component. And this is very important because, when we are looking for sequestration, in the oil industry, this is a compartment. And basically, sometimes you don't have communication with the up-deep compartment. So it's the same when we do investigation for CO2 sequestration. We need to treat this as an individual compartment, and we have to do all the characterization for that particular compartment. And for CO2 leakage, for instance, if there is good sealing capacity here, there is this fault, they don't have a great risk for CO2 leakage, for instance. Now, I'm going to be showing a set of map for the regional structure and another set of map for the sand thickness, because basically we went through the mapping, the whole trend to see the structure. everybody's, basically, you are deepening as we go to the south. And this is the Upper Wilcox. This is basically this event. I mean, this is this top here. So basically here we are mapping this top here. Now when we put the faults are a very important thing because the faults are defining the compartments. So one thing that we see is that there is a regional trends in fault in the southern portion of transect. And that's basically the big growth fault that are defining the oil and gas reservoir to the south. And there is a lot of gas, and especially in this area, there is a lot of gas and oil reservoir. And there are some oil and gas also here. And these are the compartments that are, in they are also in the kind of overpressure area. So these are things that we need to be careful when we move for sequestration in this area where we have all this faulting, because it can be deep enough to be on overpressure, and so it's a no-go area. Okay. The fault, I mean, we are still using this fault that are from 1991 because of the ascent of seismic data. We have not been able to, to do a detailed analysis of this fault. Basically, we are taking whatever was done in the past. Of course, we have some few lines, and also we are doing the well log correlation, and we had to at some point to do some kind of adjustment of some of these faults. Okay. So, but that's something that is still to do. But again, if the faults are important to create compartment for CO2, for oil and gas, they are probably not important to create compartment for CO2 sequestration because they are too deep. So basically, we are going to remap probably this fault in the area that is important for us for CO2 sequestration. So this is now for the lower Wilcox. So again, deeper into the south, and we see, oh, by the way, these are the outcrops. These are the Carrizo Upper Wilcox outcrops. And when I mentioned before, I mentioned something about the recharge. The aquifer, actually, you had this recharge of fresh water, and actually the USDW goes very deep to the south. And that is one of the problems, especially in this area, where we have more contribution of the USDW, and we are going to be looking at this in a minute. Why this USDW goes so deep? Well, I had talked to JP, that is here in the audience, in the past. Basically, there is a lot of channels, and you will see some of this channel interpretation. Basically, those channels are connecting, that recharge goes deep. So that's why, this goes, the USDW is actually kind of deep, but it's mostly in the western area. Now, this is a cross-section along, this is now along the deep, and this is an structural one to show you again this compartmentalization that you saw in the seismic line, but now how we see this with the well log. All these faults, they are, these are from the previous fault that have been done in the past, some by Edwin and some other people in the past. So basically, we are inheriting this fault. So what you see in this cross-section, from well 1 all the way to well 4 here, so you see all this down to the basin fault, and in some places, created some kind of growth. Two things important here is now the USDW. So here, this is DeWitt County, by the way. All these are in DeWitt County. And we see that within DeWitt County, so all this area here to the north of DeWitt County, these are, they may have some problems with the USDW. Actually, here, well, in this case, it is here, the USDW, so there is still room for CO2 sequestration. But that's not the case always in this area to the west, so the USDW is really deep and is taking most of the stratigraphy. Another thing here is the top overpressure. So as you can see here, I mean, the top overpressure defines the area where you can have some sequestration here, but everything below it will be a no-go area. So this part is still under analysis, so we don't really know because of overpressure analysis doesn't extend to this area. There was an study about overpressure done in the past by the US Geological Survey, but in this case we are retaking the analysis because we are using well data and we are using calculation for using sonic data, and I will show you that. Because in 2012, Bort et al., that is US Geological Survey, they define everything about the 0.7 psi per foot, that's already an overpressure. We think it is less than that. Okay, so we don't think 0.7 is close to the frac gradient. We don't think that is the overpressure is something like in 0.6. Actually, everything about the hydrostatic gradient is already overpressure. This is another cross-section, now going in the central area by Colorado County. This is from one of my former students. So if you see here again, this faulting, this normal faulting, and then you see here the lower Wilcox, middle Wilcox, and upper Wilcox. So good amount of sand, but now we had to put here well, actually the overpressure, she put here the boundary of the overpressure. So basically all these two wells are the ones that are within the overpressure. So everything from this compartment up is within the pressure compartment, the hydrostatic pressure, sorry. Now, for the sand content, we went through all these are, well, I haven't said about the amount of well, but we have thousands of wells in this project. Digital data is more than 5,000 wells already in the Petra project. So it's a lot of wells that we have been working on. Not all of them that correlated, but we had thousands of wells already correlated. So, and this is going back to the subdivision here, delta A, B, and C for the lower Wilcox. So in this case, this is the sand content, and we have a cutoff actually. I mean, the SP or the gamma ray, we do the cutoff for the net sand. That's basically, what we see here. This wedge, this delta A is all the contribution that we see, from here to here. And again, the type well, this well is not actually representing this area. It's representing mostly this area where we have, the delta A is kind of mostly mud prone. But as we move to the central area and eastern area, we see thick units. I mean, you see here, this is 800 feet of net sand. So there is a lot of sand here. And those are good for us. I mean, basically, one thing is good for us because all this area, the USDW is very shallow. It's about the top of the upper Wilcox. But the problem is another problem is the overpressure, and that's the next thing that we need to investigate. And you see here like some sediment contribution. This is the area of the Paleo Colorado and Paleo Brazos River, and these are the deltas, sorry, and these are the other Sabine deltas and other deltas there. So now for delta B, I'm changing, we change here the scale. So actually the delta B is the one that has more thickness. So you see, thickness in this area up to 1,500. So very thick sands here in this part of the central area and more or less in the eastern area. This white area that we have here, we are still adding wells there because we recently got digital wells to add, so we had to have a bigger picture of the thing. We don't extend the analysis more to the south because all this is very deep already and is in overpressure, so there is no point to go there for CO2 sequestration. This is the delta C. This is the upper part of the lower Wilcox. So again, you see in the western area, there is good amount of sand, but there is more sand in the east, in the central areas and in the eastern areas. This is not regional, these are more sub-regional, some sandstone map and depositional trends, and you see these are from the western area, these two. So basically you see this elongated feature in the delta B that is probably some kind of way reworking, because that's another problem that we have when we try to, we try to analyze this by these big packages, but delta B, for instance, it may have a lot of delta and stacking of delta. Some of them, they are way dominated, but some of them, they are tidal influence. And this has connotation for the resultant morphology and for us for sequestration too. And this is from the central area. These are in the lower Wilcox, delta B. You see these more lobate, big, giant low features. And here also in the, these are for the upper Wilcox, and we see here also some kind of lobate features. So we have a number of cores that we have been using. These are some of the cores considerations. The most important one actually is the Vogel sand, because this one here is 2,400 feet of core. Bill and Brose described that, and we have been incorporating that into analysis. We had 3 cores here in the western area. Those are the Onshore, Nagel, and Kesselin. And for the Kesselin that we have here is the upper Kesselin, the upper Wilcox. But we have also lower Wilcox. Here, this one, the Nagel, is kind of deep, and I will show you that. So basically, it's telling you that the window for storage is current here because of reservoir quality. There are 2 more cores that we are adding. I haven't described this core yet. Recently we found those one, and these are from Hardin and Jasper County, from lower Wilcox and upper Wilcox. When we see the phases of this thing, there is a huge variability in phases along this transit. So for instance, this is the Atlantis shore. So you see a stacking of channels with cross-bedding, nice sandstone. So this one, 44 millidarcy permeability, 15% porosity. This one has a lower porosity because it's in the upper part of the sand body. So this is from the Vogel sand, and these are from the description from Bill and Brose. So actually you see, for instance, this coarsening up pattern. These are wave-dominated deltas, and because there is a lot of homologic cross-bedding associated with these phases. And here we have a nice stacking of distributary channels, and basically, coarsening, finding up profiles. One thing that I did is that looking at the description of the core and do kind of reinterpretation of the phases. So I went and I did a summary of the phases in the core. So again, it's more than 2,000 feet of core. So I tried to extrapolate these things. And this is a kind of analysis we need to know also. Because when you do secondary recovery for oil and gas, you need to do this kind of thing. Because if you are injecting gas, you need to know how you are pushing the oil. It's the same thing for sequestration, because you are injecting CO2, you need to know where the CO2 is going. And sometimes, especially in a situation like the Wilcox, it's phases control. So the phases play a very important role here. So having an idea about geometries and tendency trends is very important, because we can assume how the CO2 plume is going to move. Okay? So that's why this kind of things we're expecting to expand this kind of analysis and go into the detail to this. This is basically interpretation, but it's also we use the well data. We don't have pressure data to corroborate the continuity, but basically this is a proposal. The thing is that after this, you can put in a 3D model, for instance, in a Petrel model. It's a very complex model. No? We have been doing this for the Miocene, for instance. Also. Okay, now in terms of phases and petrography, so if you see, there is a lot of porosity left in the, these rocks are quite deep, more than 10,000 feet, but still some permeability left. These are mostly subarcose and sublittorenite. We have a set of thinception for this well. In particular, you can see here very nice plagioclast feldspar and some sedimentary rock fragment. Here is cleaner. This rock is from here. So this is from the distributary channel. You still see, 16% porosity and 75% millidarcy permeability. So actually, in general, they have the quality that we need for CO2 sequestration. Jit is working with me in this project, so he's been getting this data and doing plot, and then with the phases we do calibration of the phases with the reservoir quality, and then like for instance for this well we have here, these are the phases they interpret from wells. So we see here, for instance, this is by the way, this is the porosity, the permeability plot. So decent porosity, decent permeabilities. We have here the, now when you group by facies, we have, for instance, the fluvial influence distributary channels. They are the one that has better reservoir quality. The pore throat is more than 10 microns in this case. When we go also with the shore face, the upper shore face, we see also there is nice pore throat. So these two phases are really good, you know, actually they are good for oil and gas, and they are also good for CO2 sequestration. Now when we go into this tidal influence delta from the lower shore face, reservoir quality is tend to decrease. There is more clay content in the sand. So, and also, you know, the grain size is lower grain size, so, and the multiple things basically is poor rock quality. Where? Here? Oh, this is the normalized pore volume 0.0, 0.2, 0.4, 0.6, 0.8. Yeah, more about like, because these are, you know, these are from mercury injection capillary pressure. We did it from all this core, we did mercury injection capillary pressure to evaluate the pore aperture, you know, to see, you know, how good is the rock. And this is for the Atlantis shore, and this is a small core actually. Basically, what we see here is these tributary channels and distal delta front, and there is a huge difference between them. Here also these tributary channels, again, they have more than 8 microns aperture, and the delta front, they are more, of course, poor quality. Here is the plot. There are only a few samples. That's another problem that, you know, we got this project, but we had also limited funding, so basically we had to do whatever was in the budget to do the analysis. And this is one of the wells that I showed you before, the Nagels. It's kind of deep. So this is not something that we want to target for CO2 sequestration because it's too deep. The samples are more than 12,000 feet, and I showed you a cross-section before. So basically, I mean, you see less than a micron, in this case for the middle shore face, and those are poor rock quality. So basically, there is no interest in this kind of thing. And we say middle shore face and lower shore face because that's actually what you see in the core. A lot of homocheic cross-bedding and swallic cross-bedding. So basically, it's a wave-dominated regime. This is happening. This is what is happening here in the lower Wilcox. You have those compartments. As you go away from the growth fault, it looks like the system gets more exposed to wave. So basically, there is a lot of reworking of the wave. For us, it's good because it gives you also some lateral continuity. If you are injecting CO2, you have a body, somebody that is continuous. That's more chance to dissipate both the plume and also the pressure front. But that's something that we are still to investigate because there is no work done actually for this particular case. This is the Kesselin core, and this is Upper Wilcox. So, and this is different. I mean, you see very clear the pore aperture is more microns here in the distributed channels. Lower shore face, they are still not too good, but it's basically, you know, the channels are, and that's something that we tend to expect. No, you have a system that we have a lot of distributary channels. That is actually what you are going to have the coarser sand within the distributary channels. The problem is continuity. Those distributary channels are oriented from from northwest, southeast. The structure is also to the northwest, okay? So you start injecting CO2 down deep. So how is the pressure front and the plume going to migrate? If you have a sand that is extended laterally, it's better for you. But if you have channels that are oriented to the northwest, so that's probably a problem because I mean the CO2 is going to follow those channels. But I don't have data to show you that we have not done this kind of simulation, at least with the Wilcox. We have done it with some other places. Okay, so now I'm going to talk about the constraints because in CO2 sequestration, because the geology is nice, no? You know, you see, okay, the Wilcox is it's a great system, good some kind of continuity, sandstone, thick sandstone packages, good permeability, good porosity. But now let's talk about the constraint for CO2 sequestration, because we are not in the oil business anymore. So for in CO2, we are always looking at the down deep areas. I mean, we have an structural compartment. We are not going to sequester in the up deep of the compartment where you have a lot of fault. We go down deep where we have the aquifer, the saline aquifer, and we are away from the fault. But at the same time, we are also looking into, overpressure. Are we in the overpressure, or are we still within the USDW? So this is a conceptual theme from Alex and Sue, one of their publications. So basically, that is what the government, is asking you. We have an area here. We have an injection well here. You are injecting. This is the CO2 plume, and then, but you have the pressure front that is extending farther away from the plume. Then, if you have a well here, like a leakage point, like a well with the integrity problem or a fault. So this pressure front, the pressure you create delta P, and basically you can migrate saline water, or you can migrate brines into a protected aquifer. And that's basically what the government is always asking, to watch. So that's the definition of the area of review. And there is, we can be talking for hours about this, but basically the conceptual about the USDW. The USDW, it is protected for sequestration here in the US. Everything below 10,000 ppm of TDS is protected under the regulation. So basically, we need to be very careful with that. Instead of overpressure, what the overpressure is important because, we want to be within the hydrostatic gradient, because here we have the lithostatic gradient, we have the frac gradient here. So there is a delta in between. So this is my room for sequestration, for sequestering CO2. I don't want to go about the frac pressure because I don't want to compromise the zero, okay? So basically everything that is about the hydrostatic is already here in going into the overpressure. So these are the areas that I want to avoid, okay? So how do we see that this is a transect from Ales, Cortes of Ales actually. This is going from San Antonio to Corpus Christi. And here, this is from one seismic line that he interpreted. So here are two important things, the supercritical and the overpressure. Supercritical, we need to be below 3,000 feet, is 800 meters, around that. So because we want to have in supercritical condition for the CO2. We don't want to inject the CO2 as a gas, okay? So basically we had to inject it in what is called supercritical condition. But we had this overpressure. In this case, the overpressure that we see here is mostly from the 2013 work done by the US Geological Survey. But basically we are revisiting that. So here you see, for instance, we have again here, Lower Wilcox, Upper Wilcox, Frio, Miocene. All these things, there is opportunity for CO2 sequestration. In this area is mostly here, onshore in the Lower Wilcox, Upper Wilcox, and in the Frio. So now we see here this wedge of blue, that's the aquifer. That's the aquifer. So that you see now, the aquifer is very deep. And that's a big concern actually for CO2 sequestration in this area. Now let's very quick to review the Wilcox aquifer. I'm not going to stay much here because okay, so this is Dewitt County for here, and this is the data that I've been showing you, data from there is this area. So if you see here, for instance, this is 3,000 to 10,000 ppm, still that we call moderate saline water. So there is a thick amount of dust in the stratigraphy, and saline water also. So basically, if you see below this, everything below this is already saline water. Okay, so basically, this is good for us. Now the salinity analysis, we did a salinity analysis in many wells. We got 133 wells. We went to using this equation. Basically going into the detail of investigating the total dissolved solid. And here the boundary is 1,000 feet, this is fresh water, 10,000 feet, this is salt. Everything about that is salty water, and this is USW. So basically when you see here, in this well, for instance, the base of the USDW is located here. So everything that is below 10,000 ppm here is USDW. How you see that in a well? So this is a well, for instance, and then you see this area. This is aquifer here, but then this is the 10,000. The 10,000 is this line here. So everything below that is the USDW. So, and this blue area is below the 10,000. So it is protected aquifer. So now in mapping, this is from one of my students. We are still expanding this mapping because she went to the western area. She did a mapping of the USDW. So basically here we see, I mean, these are again the Carrizo outcrops. These are the recharge of this aquifer, this deep aquifer. So what you see here is that the USDW in these counties, in Leaf Oak County, for instance, goes very deep. It can go up to 7,000 feet deep. So these are areas where basically, we don't see much, sequestration potential in this area because the USDW is deep, and like for instance here, in this particular well, okay, this is this well, so it's 6,000, and below that is very silty. So this area, the lower Wilcox is very silty. I mean, there is no sand, there's little sand, and the upper Wilcox is within the protected aquifer. Okay, so and this is a map from the Railroad Commission. Also, you can see this using well data, and this is a very important one because this is from one of my students. Tip and I, we are supervising this student. He worked for the Railroad Commission. So and if you see here the US in this area, this is again DeWitt County and Gonzales County. So the USDW, it is deep here, but as we go to the south, it's ramping, it's going up. So basically there is a lot of opportunity. He did a very nice work actually. He's presenting his thesis next Friday. So he did very nice work investigating the aquifer connectivity from the down deep to the up deep. Okay, so the overpressure, I got like 3 more slides to finish. So the overpressure is, the consideration for the overpressure is that, and very important, you see, how do we get it? We are using the Eaton equation. So these are more elaborated analysis. Actually, it's not like the US Geological Survey did in the past, using data from wells that they penetrated from Motway, actually. That was the way they did the computation of the overpressure. In our case, we are using the overburden gradient, and we are calculating pore pressure from the sonic log and some other logs. So if you see, for instance, this well and these 2 wells, you see this is the hydrostatic gradient in the sonic, very nicely here, but then you have a reversal in the sonic. So this reversal in the sonic is actually because you have more porosity, and then you have more fluid here at high pressure. So when you see the calculation of the pore pressure using the Eaton equation, so you see there is this is the hydrostatic gradient, the blue again, and these are the overpressure gradient. The comment that I made before about 0.7 psi per foot, we think that actually this is too high to define the overpressure. We think that the overpressure is defined by a lower gradient than that one. That's what we see at the moment. Now, this is from one of my students in the past, my undergrad student. So he did partial analysis of overpressure. We only gave him 29 wells in the southern portion of the transect. So basically, he did the calculation of the overpressure based in the Eaton methodology, and he mapped that. One thing that you see here, okay, this area is quite deep. I mean, so the overpressure is deep in the central area here. In the western area is, that's, you can see the depths here, more than 9,000 feet, 10,200 feet here. But as we go to the northeast, and that's something that is very concerning, because according to his analysis, it's getting shallower. For me, this is not good, and we are expanding this analysis. We want to see more wells here, and we want to reevaluate probably what is happening here, because if in this area, there is a lot of potential for CO2 sequestration in this area because there is a lot of sand. The USW is not present anywhere within the Wilcox stratigraphy. But if I have an overpressure that is quite shallow, that is limiting my window for CO2 sequestration. And this is one, but I was also comparing his analysis with the analysis that we have from BIRD, from the USW, and from the USD Geological Survey. There are some areas that they are not good match. So, I mean, this part is still work in progress, and I want to be doing more work on this because this is quite important for this area. Okay, one more thing for the constraint on CO2 sequestration. Very nice geology, you know, all the constraint in port pressure, in USDW, overpressure, but now the mechanical thing, I mean, the physical thing that you see, the legacy wells. There are hundreds of thousands of wells along the transit. There are areas that are quite, have been very extensively penetrated. And these are, wells that are, these are deep wells that goes to deeper target, because that's another problem. We have a long transit, and in many areas, we have a Wilcox stratigraphy, but the wells, they go deep because they go to the Cretaceous. They go to the Eagle 4 or other lithology for production. So we need to avoid all this amount of density well, especially there are a lot of oil wells, because there have been penetration from the 60s, from the 50s. So, and then that's the next step, is to find areas where we can find low well density so we can do some CO2 capacity estimation. We are not doing CO2 capacity estimation in this as a transit because it's not realistic. I cannot tell you that I have 10 gigatons capacity in the transit because many of the areas are going to be full of the legacy well probably with some integrity problem. So basically what we do is going to area by area and selecting areas, like in this area, for instance, this is from my former student Maria. So this is from the central area. So she found this area with, good 540 square kilometer site. And then, we go do EASiTool calculation. We have, these are pressure-based capacity. EASiTool is a very nice way to do quick capacity estimation. It was developed here in the Gold Coast Carbon Center, BEG, by Sayed Hosseini and some of his former students, postdoc. Everybody knows here Sayed. So basically these are way to do a quick computation of the CO2 sequestration of any particular area. So here, big compartments, we are not, we just do a small, let's say that this is a small project, but still you have, good amount of capacity. You see, this is 289 megaton, like in a 20 years injection, so that is a project. So that's, the other thing is basically now to know what are the economic of the project. Is it economic or not? So if you put together a number of these sites along the transit, so you tend to have a lot of capacity. Okay, now for the conclusion, I'm going to be quick here. So basically, the Wilcox Group is suitable for carbon storage. There are thick sandy units, especially the lower Wilcox. The USW is more concerning in the western area. We move northeast, and basically it's shallower, and the CO2 storage tend to increase. It's more restricted in the Upper Wilcox and Carrizo, the USW. The lower Wilcox is mostly in saline aquifer along even in the western area. Overpressure, of course, limit the area for storage, and is concerning in the northwest is concerning because it's getting shallower according to the result that we have now. So, but we had to revise that and extend the coverage of the analysis. Legacy wells, of course, limit the area for storage. Reservoir quality is mostly controlled by facies. I mean, we had diagenesis here, quartz overgrowth most of the time, but it's not more than 8%, probably based on some of the data that we have seen. So it's still a system that is mostly controlled by facies. Okay? So that was the last one, and also want to thank the sponsor from the 2025 consortium, because we are using support from them to continue with this work.
Thank you, Carlos. It's a really great summary of showing challenges for CO2 sequestration when you have an area is drilled to a Swiss cheese with low salinity, high salinity, overpressures, and so on. So it's a really, really nice summary. Thank you very much. We have time for questions. Start in the room.
I agree. Excellent work, and it's a big enchilada to chew on. A lot of, I mean, just the area alone, it's huge, and just seems like you're attacking it appropriately and diligently. It's great. My question is, up dip, the lack of mapped faults in the central and eastern part, is that a function of actual geology or lack of data or lack of, you just haven't processed that data yet?
Yeah, that's a good question, and I asked myself that question multiple times, because I think we need to revisit those areas. Probably you see more faulting in the south, because actually I think probably those are the areas, that are more potential for oil and gas in the past. They probably pay more attention to that thing, and but I think the northern area we need to revisit that, because I mean those faults are going to be very important, because any compartment that you find for CO2 sequestration, if we have fault to the north, that prevents any plume migration to the north, especially if there is if those faults are sealing. So I think it's just more to look at the data again, because GeoMap has a lot of work also done, and I was looking at some of the GeoMap regional fault trends, and I don't think they also had too much fault in the north. Yeah. But one thing, Dave, is also we need to think about this also. The amount of faulting is there is a lot of density of, the density of faulting is mostly in the area where you had a shell margin, because you had to think about the Wilcox are big wedges. When you reach the shell margin, you stack on the outer shell, you stack a huge amount of sediment. So the shell margin collapsed. So that's actually the area where you tend to have more faulting. As we move up deep in those more shallow marine settings or the fluvial channels, I don't think, I mean, the volume of sediment to create that instability is lower. That's probably also one of the things that people has not seen that much faulting also to up deep. But I think it's basically probably, that's probably geologically the reason, no? Why.
Thank you. Any other questions?
Yeah, I guess I'll second that with the, as you go inboard of the lower Cretaceous margin, I think a lot of the faults, there's deep stuff in the Eagleford, but I think they don't penetrate much higher than into the Cretaceous. Question I had, do we have a good feeling for where the wastewater disposal is going in the Eagleford play in relationship to the Wilcox?
Yeah, that's a good question. We don't have much data at the moment for the wastewater, but I have seen some data from the, especially in, I think it's in DeWitt County, the Carnes County. So they are using the Wilcox, they are using the Upper Wilcox and the Lower Wilcox to put some of that water. And that's actually data that we would like to have. And much of the data is also the companies, they have that data, they don't release that data. And then, because when that is a data that we want to have also for an idea about injectivity. Because I mean, the way if they have a good injector, for that wastewater, they inject, injectivity is high. That gives also an idea also about for us how the injectivity is going to respond to the CO2. So I think we're still, that part, it is in the idea also to incorporate whatever we got. But I don't think we had too much data also at the moment. But I have seen data from proprietary data from all companies that we cannot release. But I have seen some data. Do that answer your question?
Yeah, I mean, that is kind of the worry over there is that, you may be double dip. You may see something very perspective and then find out there's already sticking water into it. The other thing I was going to tell you, and I don't know, you may be done looking at cores and stuff. TCU has a core that Pioneer took on a shelf margin delta. It is spectacularly preserved. They encased it, so it's almost still friable. Much better preserved than any of the cores you showed there. It's a field that was probably discovered maybe 2010, early teens, somewhere in there, but they...
Which county is that from?
I'd have to look. I don't remember offhand, but it's in that Lavaca, I mean, that area that you're looking at.
Okay.
They've sold the field off, and so I think the company that bought it had no interest in the core. So it's just sitting at DC.
Okay. I'll follow up with that.
Any other questions? Is there anything online? Yes?
Great presentation. My question is about the capacity of CO2 and estimate of that based on the faulty plugged wells. Is there a good database for those compromised wells for plugging and abandonment to estimate, for example, how would be the pressure area up to that point, and based on that you estimate CO2 capacity?
Yeah, that's actually a good point there, good question. This is a first pass work, no? And then, I mean, when we do the capacity estimation, we look for areas with low density wells. And then we generate a product. If there is any company that is interested in looking at those particular areas for a project, they need to do the homework of going into the evaluating those legacy wells for integrity, okay? Because you saw the graph or the definition of the area of review. Any of those wells can compromise the area of review, okay? Because it can be, that is a leakage path, it can reduce, for instance, the area of review, and they can, any CO2, any pressure can go through moving brines by that leaky well into the aquifer. So the integrity evaluation for wells is not part of the analysis, because we need to have the data, and the data many times is coming in paper. It's coming with the well files, and we don't have access to well files. We have the digital data for the well logs, but that level of detail we don't have it, so we don't know. Many wells, we assuming that all wells, they may have some integrity problem, but it's hard to know because we don't have the data. But again, if somebody's interested in doing the work, like a sequestration site, that's something that they do. And they have to do it because the government has a regulation for that. You have to do it.
So to be clear, you can fix legacy wells.
Yeah, you can fix legacy.
And it remains a risk. We want to get funding for a study to see what the real risk is by legacy well. One can conjecture many things, but the data are not very good. So we'd like to get data. Alec Bump's working on hunting us. We hope for federal money will straighten itself out, and we'll get federal corporate money, and we'll start looking at what this risk looks like and how you remediate them. We know from EOR that you can inject CO2 with high pressure with remediated wells. We thought we'd find leaks, and Catherine Romanek and Becky Smith looked at Sac Rock 700 wells. We were terribly disappointed. There weren't any hot spots with, we could find any leaky wells. So we looked at a couple other fields. So repair is very possible. It's just a cost and remains a risk, and we'd like to use this uncertainty. So we don't know how important it is to avoid the density of penetration. It seems now the thing, but it shouldn't be. It's a risk, not a failure.
Thank you. We are right on time, so we're going to stop here, and let's thank Carlos again for this nice presentation. We'll see you back here next week. Thank you.